Okay. So so this is just to kind of remind you how strongly we are married to the idea of light as waves. But quantum mechanics, as we have seen it so far, seem to suggest that light is a particle, right? That is what the photoelectric effect and the Compton scattering tells us. Furthermore, they give us very concrete formulae where the energy of the light particle called photon is given by this formula and the momentum is given by this formula. So, what do we do? How do we choose this? So this motivates the idea of wave-particle duality, okay? It's kind of a bit of a philosophical idea. So what is the idea behind wave-particle duality? Okay, so so note that you might say that, oh, we are comparing, say, a quantum apple that is a particle, with a classical orange, right, which is electromagnetic waves. So therefore, we should not really do this. But it's actually not hard to show that even light must have a wave nature, which is quantum, okay? So what do I mean by that? So for example, take the double slit experiment. Okay, take the double slit experiment. So we can explain this very easily by classical physics. What we do is that we say that, oh, there are these two slits, and there's a photosensitive screen over here, and there is a coherent source of electromagnetic waves here. The waves go, and these slits act as coherent sources, and then there is an interference pattern here, right? You guys all know this, I'm assuming.
Yes, sir.
But this is a classical experiment, right? Because these are, we can treat them as electromagnetic waves. But what if you turn down the intensity of the source such that on average at any given time, there is only one photon in the apparatus. You know that from the photoelectric effect, the photoelectric effect tells us that, the intensity of light is proportional to the number of photons, right? Because when you increase the intensity of light, the maximum kinetic energy of the electrons don't change. What changes is the amount of electrons that are being emitted, or in other words, the number of photons that are being absorbed. So the other end of the extreme is that you turn down the source intensity so much that there's only one photon in the whole business at any given time. What happens? So, we might expect that, well, this is clearly a case where, there's only one photon in the whole business. Therefore, we are not going to get an interference. There are no electromagnetic waves here. There's only one photon. And therefore, the interference pattern that we should see is not that of the, what we should do is that the photon arrives here and it makes a ping, and then another photon goes, another one, ping, ping. So over time, there will be some pattern that will form on the screen given by the intensity, which will form some pattern. So you might think that because there's only one photon in the whole apparatus at any given time, what we will see will be just a superposition of a single photon, a single slit, and here another slit, okay? This is something you might expect. But, surprise, surprise, you already know the answer. This is not what we see. What we see emerge over time is the interference pattern that we expect and love from the wave analysis. So even though there's only one photon in the whole experiment at any given time, that photon in this experiment cannot be treated as a particle. It must be treated as a wave. And therefore, even single photon experiments where we expect quantum mechanics to kick in, there is a wave nature to it. Okay, so this is just to motivate that even even photons, even photons have a wave nature.
Sir,
So, yeah.
at first, while beaming one photon at a time, you put dot on the photosensitive screen everywhere, but photon travel on straight lines. So wouldn't there be only 2 points, one from one slit and another from another slit?
Yeah, that's basically what we should expect from here. That is the expectation, classical expectation. That's what I meant like this.
Uh, this is like the probability of
Yeah, it's like
spreading
photons
of the
going
photon.
here and photons going here, right? That's what we, roughly this is what that's what we expect. But the fact
Okay,
that
got
we
it.
see the interference pattern means that the photon does not behave like that. It does not go in a straight line.
Okay, got it.
And before Feynman path integral, there was no particle description of this. There is a particle description, but it was given by Feynman many years later, and we won't be able to cover that in this course, unfortunately. Okay. Okay, so what we saw is that even photons have a wave nature. So motivated by this, and a sense, I should say a deep sense of symmetry, the French physicist Louis de Broglie, suggested that matter particles such as such as electrons, protons, alpha particles, etc., should also have a wave nature. And although it was forgotten at the time, de Broglie, in his PhD thesis, gave a complete, more or less complete, formulation of quantum mechanics. It was this formulation, which is called a hidden variable formulation, was forgotten and then rediscovered by David Bohm many years later. However, what was not forgotten was that de Broglie suggested a wavelength. De Broglie suggested a wavelength, related to the, you've guessed it, momentum of the particle. Okay, and it's given by h bar k is p. Okay, where k is 2 pi by lambda. So this is called the de Broglie wavelength. And then de Broglie's amazing prediction was confirmed by Davison and Germer. And what Davison and Germer did is that they took a lattice of nickel. So they have a nickel, lattice. So a metallic nickel. So it's a lattice, and they shot electrons with the same energy so that they could mimic some sort of wave. And then what they found is that they found interference pattern. So these are electrons. They found diffraction pattern typical of wave diffraction. Okay? So they found diffraction pattern. And thereby they spectacularly, confirmed de Broglie's prediction, and de Broglie was given the Nobel Prize. I think Davison and Germer also got the Nobel Prize. Okay, so all of this seems like both particles, particle and light. So I should say both matter and light, they both seem to have particle nature and wave nature, right? So this led, Niels Bohr and others to formulate what is known as the principle of complementarity, or complementarity principle. Or the wave-particle duality picture.
Does this mean a speeding ball in the sky also has a wavelength?
Yes. We shall come to that. Yeah. All right. So Niels Bohr and others formulated the complementarity principle. And what does this principle say? This principle says that, there are experiments in nature, such as the double slit experiment, where one detects the wave nature of particles, wave nature of quantum entities, I should say. By the way, the double slit experiment can also be done for electrons. Okay, so it's not just like light. And there are other experiments, such as the photoelectric effect, and the Compton scattering, in which we detect the particle aspect of reality. So both are they are complementary to each other. So once so this is the principle of complementarity. It's a heuristic device at best. And Feynman criticizes it in his book on his popular book on QED, and because he had a grudge against Bohr, who once tried to explain the Heisenberg uncertainty principle to Feynman, thinking that he didn't understand quantum mechanics. So, with the formulation of quantum mechanics in terms of, say, Schrödinger equation, or the Heisenberg equation, and the Born interpretation, as we shall see, Born interpretation. Now we won't need to invoke this principle. Okay. The Schrödinger wave equation, along with the Born interpretation, makes everything very, very transparent. Okay. So I think I'm going to stop here today, and then we will have a tutorial tomorrow, unless something bad happens from now until I get the tutorial deployed to Moon. And what I'll try to do, I'll try to have another extra class, another makeup class. Then I think we will be all caught up. Okay. But before that, any questions about this?
Is it right to think of waves and particles as the same thing? Maybe in like different limits, they look different. Is that what the wave-particle duality is about?
No, it's a little bit more subtle. It's not a little. It's actually a lot more subtle. We will see that there's this thing called the wave function. It's a abstract mathematical wave, and that wave function carries in it all the information about the prediction of this, how the system is going to evolve until we make observations, and then it can only make a statistical prediction. So that's very different. So the wave here is not kind of a physical wave. That's one way of looking at it. Another way of looking at it, the Feynman picture, is that everything is a particle, but it's a highly non-local and a non-classical particle. Okay, one of the things I want to, draw your attention to, which is, this discussion, in like this sort of arguments, imply that the observer is part of the reality. They are describing. Okay? Because as we saw, you have a choice in what experiment you want to choose, right? And that means the observer becomes part of the description of the reality. Now you might say that, well, with Schrodinger equation, we don't need the wave-particle duality, so maybe we can get rid of the observer. But it turns out that the observer will still be a part of the description, because whenever we make an observation, we have to invoke what is known as the Born rule. But we'll see that.